Having discussed real numbers and the axiom of completeness, we are now in the position to talk about limits of sequences. In this video, we will explore what the limit of a sequence means. We will also show examples on how to compute limits of sequences. Here we will focus on the intuition. The actual solutions will be uploaded in separate videos, so please subscribe to be notified when they have gone online. Let us look at the following sequence, a sub n equals n. When n equals 1, a sub 1 equals 1. When n equals 2, n sub 2 equals 2, and so on. The limit of a sequence is the number that it approaches as n becomes very large. For this sequence, it is easy to see that as n gets larger, a sub n also gets larger. Therefore, as n approaches infinity, a sub n also approaches infinity. We say that for this sequence, the limit does not exist. We now look at this sequence. First, we notice that the terms in the sequence do not exceed 2. We say that it is bounded above. We also notice that no term goes below 0.5. We say that it is also bounded below. Finally, we see that as n becomes large or approaches infinity, the sequence approaches 1. We say that the limit of the sequence is 1, or that it converges to 1. For this next sequence, we observe that no term goes below 0. We say that it is bounded below. We also observe that the terms in the sequence did not exceed 1. We say that it is bounded above. And if we zoom in, we can see that each term is bigger than the preceding term. We say that this sequence is increasing. And we know from a previous video that a bounded increasing sequence converges. And indeed, we see that this sequence converges to 1. Lastly, we look at the following sequence. Again, we see that the sequence is bounded above and below. Zooming in, we see that each term gets smaller. It is smaller than the previous term. We call this kind of sequence a decreasing sequence. And because it is bounded and decreasing, it converges. And this sequence indeed converges to 0. Let us review these two sequences from the previous slides. For the sequence on the left, the limit beta is 1. For the sequence on the right, the limit gamma is also 1. If we add the two sequences, what do you think will be the new limit? It may be obvious to you that the new limit is simply the sum of the old limits. This makes sense because to find the limit of the new sequence, we only need to think about what happens as n gets very large. Because the left sequence becomes closer and closer to 1, and the right sequence gets closer and closer to 1, it would make sense that the limit of their sum will also be the sum of their limits, which is 2. In fact, we can generalize this for all other arithmetic operations. To summarize, here we explore the intuition behind limits of sequences. We got comfortable with the idea that the limit of a sequence is the number that it approaches as n gets very large. We also saw examples that affirm the axiom that says bounded increasing sequences converge. Lastly, we intuitively made the conclusion that when we apply arithmetic operations on sequences, the limit of the resulting sequence can be obtained by applying the same operations on the limits of individual sequences. In other words, the limit of the sum, the difference, product, and quotient of sequences are equal to the sum, difference, product, and quotient of the individual limits. In this case, the individual limits are alpha and beta.